Damage-tolerant analyses have the objective to determine up to what extent a structure is tolerant to damage within the structure. Take for example fatigue cracks. The question then will be at what size of the crack a structure will fail under given loads. To answer this question, the stress concentration factor Kt is inadequate. Recall that Kt was a function of the notch root radius. The smaller the radius, the higher Kt. With fatigue cracks, the crack tip is generally sharp, equivalent to a notch root radius of approximately 0. Hence, Kt becomes infinite, indifferent of the crack length. To be able to perform damage tolerance analyses, another parameter therefore is required. This other parameter is called the stress intensity factor, which is an elastic concept derived from linear elastic fracture mechanics. The stress intensity factor, or capital K, is a function of the applied stress and of the crack length. The equation for K is valid for cracks in an infinite plate, as illustrated on the right hand side. For any other geometry, this equation generally is corrected using correction factors. Cracks grow through material in different opening modes. These modes describe how cracks effectively open at the tip, which is not necessarily the same as a loading mode. One may pull a crack open in tension, which may still result in a crack surface where the opening mode is a combination of these opening modes. Because the resistance to cracking depends on the opening mode, one generally has to specify for which opening mode specifically a parameter is quantified. For example, the fracture toughness is generally defined as the resistance to fracture of a crack in opening mode 1, hence the notation K1C. In case a crack reaches a critical length with a combination of opening modes, then one should refer to the critical K with only the subscript C. The reason is that the critical K may have different values depending on the combination of opening modes, but it's considered a material property for the individual opening modes. Hence, the fracture toughness K1C has a specific value for each material. It can be used in the equation here to estimate at what stress a structure or material will fail for a given crack length. Or, after rewriting, at what crack length a structure will fail for a given applied stress or loading. Because the stress intensity factor is an elastic concept, calculation of K is only valid when plasticity is limited to small-scale yielding. In such case, material ductility is observed to influence the value of K1C. The more ductile the material, the more resistant to cracking and failure.